Does anyone want to have a try?
I'm a tricky customer.
Yeah, yeah.
Is there any tracking in this, or is it just...
No, just the discriminative part is frame-based.
I haven't broken it yet.
Yeah.
That's good.
It's about like 25 to 30 frames per second. Yeah.
That's very good. Anyone else?
Yeah.
Right.
I think we can.
I'd like to introduce you now.
Yeah.
Demo.
Yeah.
Yes, so hello. We're very pleased to have Jie here, who is studying for a Ph.D. at Imperial with TK Kim, and was previously at Tsinghua and Beijing. And as you can see, she is an expert on hand tracking and has also been very involved in the hand benchmarking projects at recent CVPRs and ECCVs and so on. Sorry, ICCV. And she's going to tell us about hands.
Yeah.
Welcome.
Thank you. Yeah. Okay, I'm very glad to have this opportunity to present my PhD work about 3D hand pose estimation using convolutional neural network. So recently, 3D hand pose estimation has gained a lot of interest with the commercial depth camera. We can see many companies has incorporated or are planning to incorporate hand interaction into their products. A 3D hand pose estimation can be formulated as configuring the pose space given the depth image. The pose space can be represented by 3D joint locations or the angles between the bones. So assume we have a data set that consists of pairs of images, input images, and its label for this image. What we can do if we want to make a prediction for a new unseen image, like we want to estimate the joint locations for the new images. Yes, we can simply learn a mapping function f from x to y. And for this function, we can choose CNN or random forest or other supervised learning method. But we will have this question: will this mapping function learn a good mapping? If not, what are the challenges? So these are the challenges. First, the hands can appear in any viewpoints, meaning complex articulations. Also, in some viewpoints, it exists severe occlusions and many self-similar paths. It's also like we have different kind of shape. Finally, acquiring a label dataset itself is a problem. So there are typically three kinds of approaches to solve this problem. The first one is the learning-based method. It is what we have discussed, learn a mapping from X to Y. It is efficient, and there's no need to do checking, and there's no need to do initialization. It's like what the demo I showed just now. But you need to store the learned function. And the second method is the generative method. We assume we have a hand model, and we search the pose parameter space to find a configuration best align the hand model to the input image. So this method, if we use a very good hand mesh models, for example, it can achieve very accurate results. But as the hand is in a very high dimensional space, it is very hard to converge without good initialization. So the third method is a hybrid method that combines the above two. The discriminative method can provide an initialization for the generative methods, like the Sharpe's and Taylor's work, and also the prediction of the learning-based method can act as a part of the energy for the generative method. So my PhD work tackles these challenges mainly by the learning-based method. The first work deals with the viewpoint, articulation, and the self-similar paths. And the final work focuses on the occlusion. And then at the same time, we collect a larger data set by design an automatic labeling system. So my first work is motivated by two observations. The first one is we have many hand poses in images. They are different just because the viewpoint changes. The second observation is though the images demonstrate complex articulations, many images share self-similar paths, like the square part. So we can use part-based method to help our learner model to generalize well to the unseen images. However, due to many self-similar paths, the model trained with the part-based method can hardly discriminate the different paths. So I can challenge you to identify which parts they belong. It's quite hard. But if we move our attention, like or estimate the hand paths by following the hand structure, like if we know this is the middle finger, and if we follow by the hand structure, we can identify which parts they belong. So for each patch, we can learn offset from the center to the following joint locations. As long as we can find some similar paths, like the similar paths in the datasets, we can estimate the patches for the new unseen images. And then when we concatenate all these patches, we can get the whole pose. Also, as we estimate the hand in a sequential way by following this hierarchy, we are able to reduce the viewpoints at the same time. We assume the palm is rigid, and we can calculate the global rotation by the estimated palm joints. So by these estimated joint locations, we can align all the viewpoints to one direction. So this reduces the viewpoint variation. So we are not the first one to use like the hierarchy or hand structure. These two work decompose the output joint locations by following the hierarchy. The difference of our work from this work is that we follow the spatial attention in image recognition to transform the input and output at the same time to reduce the input and output space variation. By feeding the model with local paths, the viewpoints, the variation of the input space is reduced. You can see the whole images, it demonstrates many variations. But for the hand paths, the variation is smaller. So if we, at the same time, we organize the parts by following the hand structure, we avoid the difficulty to discriminating the different hand paths and also make use of these self-similar paths, because the self-similar paths, and we just want to know the offsets. As long we find some similar paths in dataset, we can make an estimation for the new patches. So also for the output space, it is largely reduced. For example, if the black sphere is the pose space for the middle finger tip, if we use the part-based method and learn the offsets, the sphere becomes the brown one. And if we further reduce or align the viewpoint into one direction, the space for the fingertip is confined by the red arc. So to attend on these local patches around the hierarchy, we apply a spatial transformation to the input image and the output joint locations. The parameter of the transformation is acquired by the estimation result from the previous layers. For example, if we want to estimate the yellow joint, we focus on the patch centered on the estimated red joint locations. The txty in the transformation is the location for the red joint, and the theta is the rotation for the whole poles. And B specify the cropped size of the patch. So the spatial attention module is actually between two successive layers in our hierarchy. It transforms the output and the joint locations to a patch and align it. So if we put all the hierarchy layers together, we can get the whole poles. However, if one, like in this slide, if one of the estimator is wrong, the following estimation will be wrong. So this is error. There exists error accumulation in our method. We propose two solutions. The first one is we use a cascaded stage to refine the estimation. The second one is we use some criterion to evaluate the estimation and remove some bad hypotheses. So for the second method, we extend the self-energy of Tang's work, the work which we mentioned, by introducing the palm structure and the bone length. We generate multiple samples around the estimation of the CNN, and then use the PSO to search the minimum of the energy we use. So the whole pipeline consists of 4 layers. In each layer, it consists of cascaded stages and partial PSO, like to estimate the joint locations in this layer. A spatial attention module is added between 2 successive CNN to focus on the local patch and align input and output. So we can see after the refinement, the error accumulation is largely reduced. So to show the efficacy of each component we use in our pipeline, we provide multiple baselines. Like for the first one is a holistic CNN regressing 21 joints together. And the second one, we have separate CNN to estimate the global rotation. And then rotate all the images to one direction, and then estimate the 21 joints. For the third baseline, is we first estimate all the CNNs together, and then apply the spatial attention on some local patches to refine the estimation. The fourth and the fifth is our proposed method without the refinement or the error accumulation, and the one with the refinement.
Sorry, could you say anything about the sizes of the CNNs and the baselines?
We set the name like because we in our model we have multiple CNNs, so we set the size of the baseline CNN, the memory size, the stored memory size same with our proposed method, so they can like the size or the capacity of the CNN is roughly the same. So we can show each component we add improve the performance. This on all the data set. And here we show the viewpoint distribution by using the estimated rotations from the palm joint. So it's in different cascaded stages. So the blue one is the original distribution, and after we refinement, the rotation variation become largely reduced. So then we compared our method to many prior work, and HSO is Tang's work. It is quite similar to our method. Our ECC, this work can be treated as an extension of this work, but we can see, like in this data set and the other data sets, we improved by a large margin. So the next work is about data sets. So though the part-based method can help generalization when there is no enough data, there are still many cases we can not even find the similar parts in the data set. So we want to collect a larger data set. Sure, we can try to synthesize hand images to get larger data set, like MSRC's synthetic data set. But the synthetic images appear quite different from the real images. And it is also not easy to design very natural poses. So before big hand, the largest real data set is hand neck, but they only label 6 joints. So these two factors motivate us to design automatic labeling system with 4 hand pose as annotation. So here, I will not go into the details, but show the space coverage of our data set. The big hand data set, like this one is a viewpoints, and the second one is articulation. We can see the big hand demonstrates a broader and more even coverage when compared with ICVL and the NYU data set. So using this data set, we hold like 2017 hand challenges, and the top 3 achieve like error about 10 millimeters. And the demo I showed just now is about the similar of the top 3 is about 13 for the unseen object. So we have already got like an error as low as 10 millimeters. So does the learned function, because these functions are all based on the discriminative method. So we have this question: does the learned mapping function solve all the challenges we mentioned at the start? When we collect the data set, we consider and design our method. We consider the viewpoint articulations, but we haven't considered the occlusions. So can the mapping function work well under severe occlusions? So in this work, I want to model the hand pose and the occlusion. So before we start, let's figure out the problem first. So when we collect the data sets for the big hand, we have these observations. For many poses, for many images with occlusion, we have multiple ground truths for the occluded one. Yeah, you can see when the camera is over there, and we can get many at articulations. So the blue skeleton are the ground truths for the visible joints, and the red and the yellow is for the occluded one. So our problem becomes, if we use the learning-based method, our problem is like we're mapping one images to multiple joint locations. So what will happen if we use a CAN trained with a mean squared error? So we first look at an example image with occlusion. The red skeleton is the prediction for of the CAN trained with a mean squared error. For the visible joints, the estimation is more or less good, but for the occluded joints, the prediction is not close to any ground truth. So to further clarify our problem, we assume our data set to train the CAN contains 2 exactly the same images of A, and their ground truth is the yellow in D. After convergence, the CNN will give an estimation of the red part. It's an average of these two labels. So apparently, the average is a long estimation for articulated object. So what should we do? For the visible joints, we have multiple joint locations, and for for the visible, we have only one. For the occluded one, we have multiple locations. So we can think of model these two cases by different model or different laws. So we propose to solve this problem by a two-level hierarchy. The first, the top hierarchy is we have a binary variable to represent a joint is visible or not. If it is visible, we have a uni-model distribution to model this one. And for the occluded one, we have a uni-model distribution. And by depending on the visibility in the top level, we can switch between these two cases. So the binary variable representing whether a joint is visible or not follows the Bernoulli distribution. So when a joint is visible, we have it is actually a deterministic. But if we considering the neighbor noise, we can see the joint is drawn from a single Gaussian distribution. So we model it by a single Gaussian distribution. When the V is 0, the joint is occluded. So we use a multi-Gaussian with J component to model these multi-model labels. So with all the components defined, the distribution of the joint locations Y depend on the visibility is like this. And the joint distribution of Y and the visibility is like this. So the two-level hierarchy is shown in the conditional distribution. First, a sample V is drawn from the Bernoulli distribution. And then, depending on V, the joint location Y is drawn from the uni-Gaussian distribution or the multi-Gaussian distribution. Thus, so our proposed method can switch these two cases and provide a full description of the hand poses and occlusion. So now we have defined our model, and the next problem is how to set the parameters. Note the hierarchy mixture density is and also the joint distribution are conditioned on the input image X. And so we can see these parameters are actually dependent on X. They can be represented by a function. As the joint distribution is differentiable, so we choose a CNN to learn these parameters. So given a data set of image and these possible joint locations and visibility, the likelihood over the whole data set is the product of all the individual joints and for all the images. Here we assume all the joints are independent of each other. So our goal is to learn the neural network that yield parameters maximize the likelihood. And we use a negative logarithm likelihood as a loss function. So this loss function consists of 3 terms. The first term is about the visibility, and the second term is for the visibility visible joints, and the last one is for the joints and occlusion. So during testing, when an image X is fed into the network, the prediction for the joints, for one joint, is diverted to different branches depending on the prediction of the visibility W. If W is larger than 0.5, the prediction or the sampling for the visible joints is in the first branch, the single Gaussian. Otherwise, it's in the second branch. But the problem is that when the prediction for the visibility is wrong, the sample or the prediction for the joints will be wrong because we go into the wrong branches. So to help this Bell's problem, instead of using the binary visibility label V to compute the likelihood or the loss function during training, we use samples drawn from the estimated distribution. So when the number of the samples for the visibility is larger enough, and the average of these samples become W. So we replace V by W during training, and this we call it a soft version of our proposed method. So to demonstrate the superiority of our work, we construct two variations. The first one is a model, is a method like model all the joint locations by a single Gaussian, and the second one is using the second one is model all the joints by multi-Gaussian distribution. So in this figure, we draw 100 samples for each fingertip from all the distribution of all these methods. So for the visible joints, this line, the SGN and the HMDN actually produce compact samples around the ground truth. Well, for the MDN, we can see it's actually have a broader range compared to these ones. And for the occluded joints, well, the samples produced by SGN, the samples produced by SGN is in a broader range and is overlapped with other joints. And the samples produced by HMDN or proposed method is scattered in the movement range of the joints. So we can see the HMDN combines the advantage of SGN and MDN and is able to produce compact samples for the visible joints and interpretable samples for the joints and the occlusion. So to further demonstrate the distribution predicted by our method, we represent the distribution by the spheres. So the spheres is a component of the multi-Gaussian, and the center is the mean, and the radius is the standard deviation, and the transparency is in proportion to their mixture of different components. So we can see HMDN actually combine the superiority of SGN and MDN. So to compare these variations, we draw one samples and then compare the sample to the post label. The average error for the visible joints and the occluded joints are listed here. We can see for different number of Gaussian components, HMDN consistently improved from the SGN or MDN. And as our motivation is actually modeling the distribution and occlusion, so we measure these two distributions by sample by getting samples from the predicted distribution. We compare the set of ground truth labels and the set of the samples we draw and calculate their minimum distance and see how well they align each other. If they are quite aligned, the distance should be closer. So we can see the method we propose improved a lot from SGN for the occluded one. So for the when compared to MDN, it should achieve a similar accuracy. Yeah. So previously we proposed to mitigate the exposed bias during testing. So by sampling from the visibility distribution and training. So in this table, we show the soft version consistently achieve better results than the hard version. And when we compared with prior work, we choose a data set that contains a considerable number of occluded joints, both in testing and training. And we compare 3 methods. The first figure shows a comparison with this method using the common used measurement metric, the proportion of joints and a certain threshold. The first one is our ECCV's work, and the second one is Tang's work. Because we compare them in the red 2 figures by sampling, because these 2 methods can provide multiple outputs. And our ECCV's work is is because we're jittering around the CNN estimation, it can be treated as a unit Gaussian model. And in Tang's work, they have a GNM fit into the leaf node, so it can be treated as a multi-Gaussian distribution. So when we compare these 2 methods, we draw multiple samples and choose the closest distance to the ground truth among these samples. So we can see our method actually can achieve lower accuracy when we draw more samples, and the variance of our method is smaller than these 2 methods. So here is all my work. Thank you.
Thank you very much. I think we have time for questions.
Yeah, so in one of the tables you showed that your hierarchical HMTN method actually leads to better results on visible joints, not only on the occluded joints. So any intuition why that might be the case? So yeah.
So you mean?
Because you also have an improvement in error in visible joints, not only in occluded.
Yeah. For the visible joints, actually, you mean why it should improve on the visible joints? Yeah, it actually should have, because also in the reference in the Bishop's 1995 paper, they also showed when we model the multi-model problems using like the distribution, it help the learning for the single model occasions. So I think this is because when we during learning, when we the error from these 2 parts, from the multi-model parts is learned easily, is converged easily. So it helps the network to allocate its capacity in the visible or the single Gaussian single model part. So, but if we treat all these cases by using a single model or using a mean squared error, it actually adds the burden or maybe mislead the network to converge to a bad minima.
I just wondering if you tried extending this sort of reasoning of visibility and inclusion to the situation where you have 2 hands and maybe a second hand including first, and or maybe if you haven't tried that, whether you think how confident are you that this approach would work in that situation?
Yeah, I think it is also for I haven't tried that two hand, but like for if we one part is the difficulty is the detection part, how to discriminate these 2 parts. But once if we have got the information like the cropped one, I think it will work. But I'm not sure because it is quite complicated with just a single part, especially when you have some the occlusions. I think Taylor's like the recent work, they have deal with this slightly interaction, but also two hand. But for this work itself, it can extend to the two hand if there's no interaction. Yeah.
I was going to ask just a bit about the how the training data was labeled. I mean, did you have, for an occluded joint, did you supply multiple labels, or you supplied one per example?
Yeah, actually, because in the training, we didn't like do any like manual like supply because we just if we look at the post part, start from the label part. If we look at this label, it actually has a corresponding input image, because when we collecting it, each label has a corresponding input images, and for this we have different labels. So yeah. So during training, we didn't group any ones. We just like feed them into the training. We don't like provide because it actually exists in the dataset.
Yeah,
but for testing,
about how the data
yeah.
set was collected for the
So
data.
in the collection, we need to like perform these as many as possible.
Right, and yeah.
Yeah.
Okay.
So for the but for the testing, we need to like group some poles together using the similar like the sequence to make them like if they are very close to each other for the visible joints, we treat it these are the multiple ground truths. Yeah.
Cool.
Yeah. Thank you.
And what was the how was it annotated? The big hand, so 2.2 million depth images are recorded. I'm just not familiar. How is the ground truth attached?
The ground truth is like we have a checker star system. Like each joint is attached with a sensor,
Right.
and we have 6 sensors.
Okay.
Yeah, one sensor is attached to the wrist, and the other one is fingertip, because the sensor provides both locations and rotations, the global rotation. So if we assume the hand is the palm is rigid, we actually can calculate the other joints by the location and the rotations.
Right. So
Yeah.
in terms of data recorded, then it's actually the same as HandNet that you compared before.
Yeah.
It's just that then you fit a hand model to the 6 recorded sensors.
And we like do some inverse kinematic, like if we get this joint location, and we have rotation, we actually can calculate these parts.
So how worried are you about your ground truth not modeling individual flexions? So this and this might look very similar in your sensor data.
For the sensor data, because when you do this, the rotation actually change, because it's also record the rotation. This is this and this. The sensor is very sensible, and it can give you different rotations, and then you can calculate the other joints.
And I'm not familiar. How does the sensor interfere with the depth data at all? Like other wires that.
Yeah, we have the wires, but the problem is the thing is the wire is quite thin, and the sensor itself is thin. So in the depth camera, in the depth image, you can hardly see these wires. But in RGB, we cannot use this data.
In RGB, you would easily see them.
Yeah. So my current work is about transforming the depth to the RGB. We generate some like by some gain or something.
Mm-hmm.
Yeah.
Good. Anyone else? Right. Well, thank you very much.
Thank you very much.